Hello learners, welcome to Constant Learners. In today's video, we are discussing the concept of attribute closure. So we will discuss what is attribute closure, how do we find it, and most importantly, why do we need attribute closure? All right. And then we're going to look at some examples for the same topic. But before we begin, if you haven't already subscribed, please subscribe to the channel and give this video a thumbs up if you think it has been useful for you. Let's get started. Now, what is attribute closure? Let's say we need to find the attribute closure of X. Now, attribute closure is denoted as X plus, right? And it is a set of attributes that can be determined from X. So, we've already discussed what is functional dependency. In functional dependency, we have an attribute on the left hand side, that is the determinant, right? And on the right hand side, we have the dependent, right? So we say that A determines B. Now, whichever attributes can be determined from X, the set of those attributes is known as attribute closure of X. All right. Let's say X can determine the attributes A, B, C, X, and Z, right? So this entire set of attributes is known as attribute closure of X. All right. So whichever attributes can be determined using X, or whichever attributes are directly or indirectly dependent on X. So all of these attributes can be functionally determined using X, right? So we can say that they are directly or indirectly dependent on X. This set of attributes is known as closure set of attributes, right? Now, how do we find this? That we are going to see in a bit. Now, another important point is how to find attribute closure. Let's take an example. Let's say we have a relation with attributes A, B, C, and D. And the functional dependencies given are, we have A determines B, then we have B determines C, and C determines D, right? So these three functional dependencies are given for this table. Now, in the previous videos, we have discussed what is functional dependencies and what are the properties of functional dependencies. We are going to use those properties here to find the attribute closure, right? Now, let's say we have to find the attribute closure of attribute A. We write it as A plus. Now, as per the reflexive property, we studied this in the previous video. An attribute can determine itself. Of course, if it is a roll number will be able to determine the roll number itself. Name will be able to determine name itself. So A can determine A itself, right? Now, we'll check the functional dependencies. Here it is given that A can determine B. So then A will also be able to determine B. That's right. Correct. Then we are given that B determines C. Now we studied about the transitive property, right? What is transitive property? That means if an attribute determines a second attribute, and this second attribute determines the third attribute, then this third attribute will automatically be determinable by the first attribute also, right? So C will also be determinable by A. Yes. Now C determines D. Again, as per the transitive property, D will also be determinable by A. Alright. So we are getting all the attributes can be determined by the attribute A. So this set of attributes is known as attribute closure. Now similarly, we can find the attribute closure for B. Quickly, let's do it. B will determine itself. Then it's given that B determines C. And since C determines D, we can have D also here, right? Then for attribute closure of C. Now anywhere here we cannot determine A, right? No other attribute is determining A. So the attribute closure of B will not have the attribute A in this, right? For C, C will determine itself and C can determine D. But now D cannot determine A, D cannot determine B. So we will not have A and B here. And finally the attribute closure of D will be just D, because there's no other functional dependency given where D is determining any other attribute, right? So these are the attribute closures of A, B, C, and D. Alright. Now we can also find the attribute closures of a set of attributes. Right. That means A combined with B. Attribute closure of A, B will be, see, A will determine itself and B will determine itself. Right. Then A determines B. B is already here. B determines C. So we'll get C here and C determines D. So we'll get D here. Right. Attribute closure of CD. Again, C will determine itself and D will determine itself. Now here also C determines D. There's no other attributes that can be determined from these combination. So this is how we find the attribute closure. Correct? Now, why do we need attribute closure? Why do we need to find attribute closure? What is the purpose? To find the super key and the candidate key. We are using attribute closure to find the super keys and the candidate key. Now, super key out of these attributes, we found these attribute closures, right? Out of these attributes, which attributes can be selected as the super keys? So, any attributes that can determine all of these attributes, A, B, C, and D, those attributes are selected as the super keys. Now, here in this case, we are getting A, B, C, D. That means all the attributes are being determinable by attribute A. So, A will be our super key, right? Then again here, we're getting A, B, C, D with a combination of A and B. So, combination of A, B will also be a super key. Now, when we discussed super key, I explained you that a combination of super key with any other attribute will also be a super key, right? Now, since A is a super key, a combination of key with any other attributes, that is B, C, D, will also be a super key, right? So, A, C will also be a super key. A, D will also be a super key. Now, AB is a super key. So, a combination of AB with any other attribute will also be a super key. So, ABC will also be a super key. ABD will also be a super key, right? ACB, that's already done. ACD. ACD will also be a super key. Yes? Then, a combination of all four attributes, that is A, B, C, D. This will also be a super key. Yes, of course it will, right? But out of all of these super keys, which key do we select as the candidate key? So in the video where we discussed candidate key, that is how do we decide which key will act as a candidate key. There I discussed that candidate key is the minimal super key. Minimal super key means what? That means the combination should not have any other super key in that, right? That means the subset, the proper subset of those key should not be a super key. Now, if we take the proper subset of AB plus, right? Proper subset of this will be A and B, right? Now, A itself is a super key. So, then this cannot be a candidate key. A minimal super key is the one that does not have any other super key in this. That means that super key should not be made with any other super key. So, here, if we look at this combination, A, B plus, in this A itself is a super key. A itself is a super key. A itself is a super key. Here again, A is also a super key and AB is also a super key. So all of these combinations cannot be selected as a candidate key. So the only eligible attribute here is A. So our candidate key here will be A. Alright. Attribute closure of A gives us all the attributes available in a relation and thus that is selected as a super key. And since it is a minimal super key, it is selected as a candidate key. I hope that this topic was clear. Now let's take some examples to understand some shortcuts to find the super keys and candidate keys. Now, first important point that we need to remember is any attribute that is on the right hand side of the given functional dependencies will always be determinable. Some way or the other, they will be determinable, right? Like in this relation, PQRST, the functional dependencies given are P determines Q and R determines T. So Q and T are on the right hand side of the functional dependencies, right? So we don't need to worry about Q and T. Somehow they will be determined, right? We need to worry about these attributes P, R, and S because they are not present as dependents anywhere in any functional dependencies. Now we know that an attribute can determine itself, right? So any attributes that are not present on the right hand side, we can keep them on the left hand side. How? See, here P, R and S. These are not present on the right hand sides, right? So we can take P, R, S, the attribute closure of P, R and S. Now here P will be able to determine itself, right? And it's given that P determines Q. So we've got P and Q. Then R will be able to determine itself. So we get R here, right? Then S will also be able to determine itself. And it's given that R determines T. So we'll get T also here. So this now becomes our super key. Alright. Now, if I add any attribute to this, let's say we take PQRS, the attribute closure of PQRS. So PQRS, they will be able to determine themselves, right? And R can determine T. So this will also become a super key, right? If I take any combination of attributes here along with P, R and S, so that will act as a super key. But here in this case, which one will become the candidate key? The candidate key will only be P, R, S, right? Because this attribute closure is giving us all the attributes, that is able to determine all the attributes, and hence it is the minimal super key, and thus it will act as a candidate key. Now in this case, the functional dependencies given are P determines Q, Q determines R, then RS determine T and T determines P, right? So the attributes on the right hand side are Q, R, T and P. Q, R, T and P. So we don't need to worry about P, Q, R and T because they are present on the right hand side of the functional dependency. Some way or the other they will be determinable. We only need to worry about S, right? So a combination of attribute S with any of these attributes will act as a super key. Let's see if that works or not. See, here let's take the attribute closure of P and S. In this case, P will determine itself, right? Then P can determine Q because Q is functionally dependent on P. Then Q determines R. So we also get R here. Then S is already present here. S will determine itself, right? Then a combination of RS. We have a combination of RS here on the right hand side. Now, if we have a combination of RS on the right hand side, then whatever attribute it can determine, that will also be determinable with this combination, right? So, the attribute closure of PS is giving us all of these attributes. Similarly, if we take a combination of any attributes, that means let's say we take the attribute closure of QS. Now, Q will determine itself and S will determine itself. It's given that Q determines R, so we get R here. Then combination of RS will determine T, so we get T here, and T determines P, right? So this will also act as a super key. RS will also act as a super key and TS will also be a super key because all of these combinations will give us all the attributes present in the relation, right? Now, if we combine these attributes with any other attributes, that means let's take a combination of P, S and Q. Let's find the attribute closure of PSQ. Now, we know that PS in itself is a super key, right? All of these are super keys. PS in itself is a super key. Then this combination will also be a super key. Of course it will. P will determine itself. Q will determine itself. S will determine itself. Then Q can determine R. So we get R here. Then a combination of RS will determine T. So we've got P, Q, R, S, T, right? So this will also be a super key. But in this case, we are getting four minimal super keys. First is PS, then QS, then RS, and TS. So we are getting four minimal super keys. So out of these four minimal super keys, we can select any one as the candidate key. Let's see if I'm selecting PS as the candidate key, right? Now in this case, we again get two other concepts, that is prime attributes and non-prime attributes, right? So prime attributes are the one that are used to form the candidate key. So in this case, P and S are used to form the candidate key. So they are the prime attributes, and non-prime attributes will be the ones that are not being used to form the candidate keys. That is Q, R, and T are the non-prime attributes, right? So this is how we can find the super keys and candidate keys using attribute closure. This concept will be very useful to understand the normal forms. So I hope that this concept was clear. If it was, please give this video a thumbs up, subscribe to the channel, and thank you so much for watching.